Good morning, students. In the last class, we discussed about the Coulomb's force, right? So now, what is Coulomb? For 1 mark, is important. Define Coulomb, right? So from the Coulomb's law, we have two charges, right? So taken one as Q1 and another charge as Q2. It is separated by a small distance. So it exerts a force. That means Q2 exerts a force on Q1 and Q1 exerts a force on Q2. Right? So what is Coulomb? That means Coulomb is a charge that is 1 Coulomb of charge placed at a distance of 1 meter, right? So if we call this one as 1 Coulomb, taken Q is equals to 1C, right? So 1 Coulomb is a charge placed at a distance of 1 meter in vacuum or air, by a same charge. Same charge is nothing but similar to the charge Q, right? So here also it has 1 Coulomb, right? Then it experiences a force or it exerts a force of repulsion. So force of repulsion is important because both are same charges. That is, it exerts a force of repulsion that is equals to 9 into 10 to the power of 9 Newton, right? So this is the definition of the Coulomb, right? So we have F is equals to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R square, right? So we know the value 1 divided by 4 pi epsilon naught, it is 9 into 10 to the power of 9. So here the given condition Q is 1 Coulomb and here also 1 Coulomb, right? So here 1 into 1 divided by, so these two charges are separated by a distance that is 1 meter. As these two are similar charges, that is Q1 is equals to Q2, that is equals to 1 Coulomb, right? So charges are same, then there is a force of repulsion, right? So if you multiply all these values, we get force of repulsion is 9 into 10 to the power of 9 Newton. Right? So this gives the definition of the Coulomb. So it is important for 1 mark. Several times they are defined Coulomb. Right? So for that, 1 Coulomb is the charge placed at a distance of 1 meter of same kind from similar charge or same kind of charge, similar charge in vacuum or in air. It experiences force of repulsion is 9 into 10 to the power of 9 Newton. So this is the definition of Coulomb, right? So here the important is force of repulsion. There is no force of attraction. So that gives the definition of the Coulomb. So if we studied in third chapter, again we can define Coulomb by some other definition in terms of current, right? So here we are studying about the charges, so we define Coulomb in terms of force, that is by using the Coulomb's law, right? So next, limitations of Coulomb's law. So what are the limitations of the Coulomb's law, right? So the first limitation is Coulomb's law, that is, it is applicable for the point charges at rest. So it is only applicable for the point charges when those are at rest. So what is point charge? right? So point charges is nothing but the size of the charge is very small compared to the distance of separation. Those kind of charges we call as point charges, right? So what are point charges? The size of the charge is very less compared to the distance of separation between the charges. So this one we call as point charges. That means the size of this charge is very small compared to that of the distance. So in the last class we solved the problem, that is these two are separated by some distance, that is 2 meter, but the size of the charge is how much? 10 microcoulomb. So 10 microcoulomb, it is of the order 10 to the power of minus 6. So this size is very small compared to that of the magnitude 2, right? So this kind of charges we call as point charges, and it is only applicable at rest, right? So this one is the first limitation. So next, the second limitation is, so it is applicable when distance between the charges is less than 10 to the power of minus 15 meter, right? So if the distance between the two charges is, the maximum value is the distance between 10 to the power of minus 15. So above that distance, the Coulomb law will not work, right? So these are the two limitations of the Coulomb's law, right? So this is about the force due to the charges. That is first topic we discussed, that is force. So next here we are going to discuss the next one is field, electric field, or simply we call that one as the field, right? So what are fields? So again from the Coulomb's law, we have the charge here, right? So taken this charge as Q, and again one more charge somewhere here. So that charge will be taken as Q1 or Q0, right? So from the Coulomb's law, this charge Q exerts a force on Q1, right? So as these two are positive charges, there is a force of repulsion, that is force on Q1 due to Q, right? Similarly, this charge Q exerted the force, that means it experiences the force by the charge Q1, right? So that is by the Coulomb's law, right? So if we remove this charge, so if we remove this charge, then what will remain here? So if we put any one charge here, then this charge experiences a force that is caused by the charge Q, right? So how it is producing, that means how it experiences the force, right? So as in the last year we discussed, if there is any object, if we move this object, means we are applying the force either by push or pull. That means these are the contact forces. If we push the object, means it will displace. That means this object experiences the force by applying the push. But here this charge experiences the force, but this charge will not kept in contact with this Q, right? So this Q will not go and touch this Q, right? But also it experiences the force. To study that one, the scientist starts the new concept. So that concept is the field. That one is the electric field. So what is electric field? So electric field is the space around the charge where it exerts a force on another charge, right? So what is electric field? Electric field is the space around the charge, right? So here we are considering this charge Q. So here the surrounding of this charge is called the field, right? So in this field, if you place any charge, then that charge experiences the force. So that concept we call as the field, right? So what is field? The field is the space around the charge where it exerts a force. So if we place anywhere in this space, so if you place any charge here, then it exerts the force on that charge, right? So that concept we call as electric field, right? So consider the charge Q, right? So consider a charge Q. So placed at the origin, right? So now place one more charge. So somewhere here, right? So that charge will be taken as Q1 or Q0, right? So again from the Coulomb's law, this Q0 experiences a force that is caused by the charge Q that is in the line joint, right? So the force is in this direction, right? So now the electric field here, it is in the origin, then the distance from here is the vector r. So now if we define the electric field in the mathematical form, that is electric field is defined by E, so it is also the vector E is equals to 1 divided by 4 pi epsilon naught. So this electric field is caused by the charge Q. So hence we are taken here the charge Q divided by the distance is r square, and r cap is the unit vector which gives the direction of the electric field, right? So this one is the mathematical form of the electric field, right? So now as we say, this gives the magnitude and r cap is the direction. So in which direction this electric field exerts? So electric field exerts at any point on the charge is in the direction of the force. So electric field is also in the direction of the applied, that is exerted force. So force ಯಾವ direction ಅಲ್ಲಿ ಇರುತ್ತೋ in the same direction we are going to take the electric field, because the field exerted by this charge on Q0 produces the force F. So that's why we are taken in the same direction as that of the force, right? So now from Coulomb's law we know the force exerted by the charge Q0 due to Q. We can write F is equals to 1 divided by 4 pi epsilon naught Q into Q0 divided by R square into R cap, right? So as we know the electric field is 1 divided by 4 pi epsilon naught Q divided by Q square, right? So this term we can write F is equals to E into Q0 into R cap, right? So R cap is in the same direction, we can write F is equals to E into Q0. So we need E, that is E is equals to F divided by Q0, right? So this we call as electric field strength. So electric field strength E is equals to F divided by Q0. That means force acting per unit charge. So how we define electric field strength? So electric field strength is defined as force acting per unit charge, right? So here is force divided by the charge Q0, right? So that one we call as electric field strength, right? So the unit of electric field strength, that is E, is SI unit Newton per Coulomb, right? Next, as we say, the electric field is a vector. It has, we get the magnitude here. So this gives the magnitude, direction. How we represent the direction, right? So electric field at any charge Q. So here this Q is space surrounded by the field Q, right? So those are represented by the electric field lines. So in space The electric field lines is in three dimension. That means in all the direction it exerts the field, right? So these lines are the electric field lines, right? So how we represent the electric field? So electric field is represented by, so electric field is represented by electric field lines. So these are the electric field lines, right? So now what are electric field lines? So electric field lines are the imaginary lines. So these electric field lines are the imaginary lines. So electric field lines are the imaginary lines. So at any point, if we draw the tangent, then that tangent gives the direction of the electric field, right? So there is a difference in electric field lines and to that of the electric field, right? So at any point, on the tangent at any point on the electric field line gives the direction of electric field, right? So this concept is very important, that is electric field, because from this topic only we are getting the problems. So this year also they ask the problems on this topic, right? So we need to understand electric field. So what is electric field? So it is the space or region surrounded by the charge, either any of the charge, right? So that field exerts a force when we place a charge, that we call as electric field, right? So here this charge Q, that is the charge which exerts a electric field, right? So that charge we call as source charge, right? The charge which exerts the electric field, so that charge we call as the source charge, and the charge which tests the source charge, so that charge we call as test charge. So here Q naught is the test charge and Q is the source charge, right? So what are source charge? The charge which exerts the electric field, right? So if we taken Q as the source charge, then here we have the electric field, right? Then here Q becomes the test charge, right? So the electric field which exerts by the charge, so that charge we call as the source charge. Then what is test charge means? The charge experiences the source charge. It is used to test the source charge, right? So that charge we call as the test charge. Next, the representation of the electric field is by the electric field lines. So what are electric field lines? These electric field lines are the imaginary lines, right? So these are the imaginary lines. So if we plot or if we draw the tangent at any point on these electric field lines, then that point gives the direction of the electric field, right? So electric field is in the direction of the force. That means E direction and F direction both are in the same direction, right? So if we take a test charge as minus, then electric field is in this direction, because the force of attraction between these two charges is towards the charge Q, right? So if it is minus, then electric field is towards the source charge. If it is plus, then it is away from the source charge, right? Next, here we have the electric field intensity. So this one is very important relation. So this will be further used in next chapters, right? So whenever we need to find the force when the electric field is applied, then we can write force is equals to Q into E, right? So this is the relation to calculate the force, right? Next, here is the electric field lines. So these electric field lines has some characteristics, right? So we will discuss that one. That is characteristics or properties of electric field lines. Properties of. So this one is very important. So this is also for 3 marks. So several times they ask these properties for electric field lines, right? So there is a difference. Properties of electric charge, possibility of asking, and also the properties of electric field lines, right? So the first property is the electric field lines, or basically field lines. The electric field lines starts from positive charge, and ends at negative charge, right? So if there is only one charge, then starts or ends starts and ends at infinity, right? So this one is the first one and the important one. So as we have said, the electric field lines or starts from the positive charge, right? So if you draw this diagram, this one is the positive charge, then starts from positive charge means the direction is diverging, right? So starts from positive charge means from here, that means diverging. From this point, all the electric field lines are moving away from this charge, right? So this is for the positive charge. Next, for the negative charge, so these electric field lines are converging. That means these electric field lines are meet at one point or converging. So here for positive we call diverging, and here for negative we call this one as converging, right? So next here it says if there is only one charge, they starts and ends at infinity. That means, so here we have the positive charge. Here starts from positive but ends at infinity. If we consider only this positive charge means it is starts from here, but these electric field lines are ends at where it will end? It will end at infinity, right? So here converging, that means the electric field lines are started from infinity, but they are converging at the negative charge, right? So here for the first statement, if we return plus charge, that is plus q, and here is the minus q, then electric field lines are starts from positive and ends at negative, right? So arrow marks are very important, right? So this is the first property, right? So starts from positive charge and ends at negative charge, right? So next, the second property is in a charge field region, electric field lines are continuous, right? So here these charge field lines are continuous because there is no interaction in between the two charges, right? So that one is the second property. In a charge field region, the electric field lines we are taken as continuous, right? So next, the third one is this one is important for 1 marks also. They ask several times. They ask for 1 marks, right? So electric field lines never intersect each other, right? So they ask for the reason why the electric field lines never intersect each other, right? So for that, if we consider electric field lines, right? So if we consider, so I will consider this one as one electric field line, right? So I will consider one more electric field line like this, right? So these are the two electric field lines. As in the definition only it says electric field lines are the imaginary field lines. So if we draw the tangent at any point on these electric field lines, that point gives the direction of the electric field, right? So here I consider one electric field line, right? So I will draw the tangent at this point, right? So this tangent gives the electric field E, right? So at this point, if I draw the tangent, so this tangent gives the direction of the electric field, right? So next, in the similar way, here, somewhere here, I will find the electric field direction. So this is in this direction, right? So anywhere, if I draw the tangent, so if I draw the tangent here, then this gives the electric field direction at this point, right? If these two electric field lines are intersecting, right? So this is first one. So this one is the second one, right? Now, if I draw the tangent at this point of intersection, right? So for this curve, if I draw the tangent means electric field in this direction, right? So for the second curve, at the same point of intersection, if I draw the tangent, then it will use the electric field direction. That means at the point of intersection, we are getting two directions of the electric field. So this case is not possible, right? So hence the electric field lines never intersect. So if they intersect, then we get the two directions, right? So which is not possible, hence the field lines are never intersect. So this they ask for 1 mark. While the electric field lines never intersect each other, right? So if they intersect, so the reason is if they intersect at the point of intersection, we have two directions of electric field. So which is not possible. So hence these two electric lines, that means two electric field lines never intersect each other, right? So next, fourth property, electric field lines do not form closed loops. So the reason is that is due to conservation of charge, right? So these are the four properties. If they ask for 3 marks, we need to write any of the 3 statements, right? So if they ask for 1 marks in the reason case means they ask the third property, right? So this topic is very important. So each and every topic is very important, either for theoretic theoretical or for the problems, right? So next here we draw for plus and minus q charge. So if written same for plus and plus or minus and minus. So here we have plus q charge. Here also we have plus q charge, right? So electric field lines. So in this like electric field lines will be formed. So these are imaginary. So actual there will be no lines formation like this. So for the study purpose they considered the lines will be in this form, right? So these are the properties of the electric field lines, right? Next. Electric field due to multiple charges. So this is similar to that of the force due to multiple charges. So electric field due to the multiple charges. So problems always comes from this topic, right? So considering a system of charges, right? So here we have Q1, somewhere here we have Q2, and somewhere here we have Q3, right? So we need to find the electric field at somewhere here point, because this point has P. We need to find the electric field at this point due to system of these three charges, right? So the distance from Q1 to P, we take an R1P, that is vector, displacement vector. So similarly, from Q2, it is R2P. So in the same case, R3P, right? So here it exerts the force by Q1, Q2 and Q3 in the same manner. It experiences the electric field due to Q1, Q2, Q3, right? So as we know, the formula for electric field E is equals to 1 divided by 4 pi epsilon naught Q divided by R square into R cap, right? So now electric field due to the charge Q1, so that becomes E1 is equals to 1 divided by 4 pi epsilon naught Q1 divided by R1P square into R1P cap. So here positive charge, so always we are taken testing charge in the positive only, right? So these two are the positive charge, then force direction is repulsive. So as the electric field is also in the direction of the force, so here we are going to discuss about the electric field. The electric field is in this direction, E1, right? So next, in the similar case, E2, that is equals to 1 divided by 4 pi epsilon naught Q2 divided by R2P square into R2P cap. So that means P experiences the electric field due to charge Q2. So here also the repulsive force. So the electric field E2 in the direction of the force. Next, from the third charge E3, right? So that is equals to 1 divided by 4 pi epsilon naught Q3 divided by R3P square R3P cap. So this gives the direction of the electric field. So here we have Q. So this is E3. But we need to find the electric field at the point P. So these are the electric field due to the charges Q1, Q2, Q3. So we need to find the resultant electric field. For that we have E as E1, E2, E3. All these three are the vectors. The resultant electric field E at point P, that is equals to vector sum of E1, E2 and E3. Right? So now we know E1, E2, E3. So substitute here 1 divided by 4 pi epsilon naught Q1 R1P square R1P cap plus 1 divided by 4 pi epsilon naught Q2 divided by R2P square R2P cap plus 1 divided by 4 pi epsilon naught Q3 divided by R3P square into R3P cap, right? So in all these three terms we have the common is 1 divided by 4 pi epsilon naught. So the remaining is Q1 divided by R1P square R1P cap. So same procedure as we did in force due to the multiple charges. So this gives the electric field intensity due to multiple charges. So if there are n number of charges, so somewhere here we have further we need to, here we have the direction, we need to remove all these, then this gives the resultant electric field E, right? So this will be understood by solving the problems, right? So if we find this one in the general form for n number of charges, that is En, that is equals to 1 divided by 4 pi epsilon naught summation of I is equals to 1 to n, here it is Qi divided by R1I square R1I cap. So this gives the general form, right? So if we substitute right? So IP here also from IP, right? Now if we substitute I is equals to 1, then Q1 divided by R1P square into R1P cap. So we get the first term. Now if we substitute I is equals to 2, so here we get R2P. Wherever I, we keep going on substituting. If we have 10 charges, then we need to substitute up to 10, right? So this is due to the electric field due to multiple charges, right? So now move on to the problems based on this topic. So this year only they asked the problem, right? So this year they asked very simple problem. So all forces and electric field, these are vectors. So we need to be very careful while solving the problems, right? So March 2020, this year. 2-point charges. This question is also repeated. So in 2017 or in 18 they asked the same problem, but the numerical value is different. 2-point charges. QA is equals to 5 microcoulomb and QB is equals to minus 5 microcoulomb are located at A and B, separated by 0.2 meter in vacuum. So here we have two questions. What is the electric field? What is the electric field at the midpoint O of the line joining the charges of the line joining the charges. So next, second one, if the negative test charge of magnitude 2 nanocoulomb is placed at O, what is the force experienced by the test charge? Right, so this is the question. So they mentioned two charges. So calling this one as A. So somewhere here B. So without plotting the diagram, you can't get the proper answers, right? So we know the formula, but direct substitution and simplification may go wrong, right? So because here along with the magnitude, we need to find the direction also. So here we have two charges A and B. So taken, the given QA is equals to 5 microcoulomb, that is 5 into 10 to the power of minus 6 coulomb, and at B we have QB, that is minus 5 into 10 to the power of minus 6 coulomb, right? Next, these two are separated by the distance is how much? That is 0.2 meter. That means R is equals to 0.2 meter, right? So next, in first question, what is the electric field at the midpoint O of the line joining the charges, right? So the line joining the charges means the straight line is drawn from A to B. At the midpoint means exactly at the middle. So they mention that point calling as O. We need to find the electric field at O, right? So this is from the electric field due to multiple charges, as we discussed in the last topic. So here we have one charge, here we have another charge. So combining these two charges, here we get the electric field. We need to find that electric field, right? So first we find the electric field at O due to charge QA, right? So for first one, EA, that is due to charge QA, electric field at O due to charge A, that is EA, that is equals to 1 divided by 4 pi epsilon naught QA divided by R square, right? So this, at this point, the test charge always, we told that the test charge is always taken positive, right? So 1 divided by 4 pi epsilon naught, we know the value 9 into 10 to the power of 9 into QA value they given 5 into 10 to the power of minus 6 divided by R value they given 0.2 meter. But this one is the total distance between A and B. But here we need to find this distance AO. So this is exactly at the middle means that is 0.1 meter. So 0.1 can be written as 10 to the power of minus 1 whole square, right? So now if we simplify this, 10 to the power of minus 1 whole square, it is 10 to the power of minus 2. So if it goes to the numerator, it becomes plus 2, right? 9 into 10 to the power of 9 into 5 into 10 to the power of minus 6, this becomes plus 2, right? So here it is 9 5 45 into 10 to the power of plus 9 minus 4, right? It is 10 to the power of 5 Newton per Coulomb. This gives the magnitude, but here we need to find the direction. That is along OB, because this is positive, here also positive, there is a repulsive force here. This gives electric field E, right? Next, electric field at O due to QB, right? So same wise, EB is equals to 1 divided by 4 pi epsilon naught QB divided by R, this one as A and here is RB square. So here the value is 9 into 10 to the power of 9. QB value is, only we have taken the magnitude, 5 into 10 to the power of minus 6 divided by 10 to the power of minus 1 whole square, right? So both the magnitudes are same. So we can write 45 into 10 to the power of 5 Newton per Coulomb along, we need to mention the direction, right? So this is positive charge, here we have negative charge. So there is a force of attraction between the charge, test charge and to that of the charge B. That means the electric field is in the direction, so this gives EB. So EA and EB both are in the same direction, right? So we need to find the resultant electric field intensity at O, right? So the resultant electric field intensity at E, that is equals to EA plus EB. So as these two are the vectors, we can't directly add EA and EB. So here direction matters. So that is, from the vectors we know the resultant R is equals to square root of A square plus B square plus 2AB cos theta. So if we have two vectors, so this one is vector A and here we have vector B, right? So these two vectors are in the same direction, means these two vectors are parallel. That means angle between these two vectors is 0, right? So as theta is 0, then cos 0 is 1. Then here it is A square plus B square plus 2AB. So this can be written as A plus B whole square. It is under the root. So square and square root get cancelled. Then resultant R can be written as A plus B, right? So in the same way, here also EA and EB are parallel. That means angle between those two vectors is 0. Then we can directly add these two, right? So 45 into 10 to the power of minus 5 plus 5 plus 45 into 10 to the power of 5, right? So given 90 into 10 to the power of 5 Newton per Coulomb. So along OB. So here also mentioned along OB. So the resultant will be in the same direction like this. So if it is EA, EB, then the resultant is E is equals to EA plus EB. Right? So this gives the electric field E, that is 90 into 10 to the power of 5 Newton per Coulomb. So this is the answer for A. Next, for B, we know F is equals to Q into E, right? So in the second question, if the negative test charge of magnitude 2 nanocoulomb, that means at O they placed 2 nanocoulomb, that means minus, right? So here the Q value is 2 into 10 to the power of minus 9. The electric field value here 9 into 10 to the power of 6. So 9 into 10 to the power of 5 can be written as 9 into 10 power 6, right? So we get 9 into 2, 18 into 10 to the power of minus 3 Newton, right? So this gives the force. So take one problem has homework. So this one is also repeated in 2018. Same problem. Here they given 3 microcoulomb. Here minus 3 microcoulomb. So here they given the charge of magnitude 1.5 into 10 to the power of minus 9 coulomb. So these two are separated by a distance 20 centimeters, right? So take as assignment is for. Similar problem, methods all are same, right? So next class we will continue. Thank you.